Topics number 6 on capacitance and electrostatic energy. The learning outcome from this topic. So what you expect to know at the end of this, you should be able to understand what capacitance is and find it for simple structure. And you should be able to list the different practical types of capacitors and their limitations, and use capacitance to find energy stored in electrostatic field. Okay, so these are the things that I expect you to understand or able to do at the end of this lecture or at the end of this topic. I'm sure you know what is capacitance. You have used capacitor before. You might not have learned the internal or how capacitance come about. Okay, so this will be the lecture you learned of why or how capacitors come about. Definition of capacitance. So for two conductor systems, but not limited to just simple two conductors, it can be applied to more complex systems as well. So this is how we define it. So suppose we have a potential difference V applied between two conductors by connecting them across a power supply. Okay, so we have two conductors, applied a power supply across them, and the two conductors are separated either by free space or there is dielectric materials between them, or a mixture of both. Okay, so I have my two conductors. I apply voltage between them. The separation between them could be air, dielectric materials, or mixture of air and dielectric materials. So if I have two conductors separated, if I apply a power supply, then I will end up with a positive charge on one side and negative charge on the other side eventually. Okay, so starting from non-charge, and when we apply the power supply, and then charge will start to build up on the conductors. It will be an opposite polarity but same magnitude, okay, eventually. So the definition of our our capacitance for these systems, C will be equals to the charge divided by the potential difference. C equals to Q over V. Okay, so this is our first equation, our definition of capacitance, or Q equals to CV. And this might be the equations that you have come across previously. Okay, so Q equals to CV or C equals to Q over V. So the capacitance is a scalar quantity. Okay, so charge is scalar, and then the potential difference is also a scalar. The unit is in farads, I'm sure you know that. So the capacitance, the unit for capacitance is in farads. But if you look at the definitions, our charge is in coulombs, our potential difference is in watts. So it could also be coulombs per watt. But this is not the common unit that you use. This is the common unit, farads. The capacitance only depends on the conductor geometries and the sort of materials which we fill the space between them. So depend on these conductors and then the space between them. Capacitance is it gives us a measure of how efficiently a conductor systems can store electrical charge. Okay, so the capacitance, the value of the capacitance tell us how good that systems can store electrical charge. So if you have very high capacitance or a capacitor that have very high capacitance, which means that it can store more charge compared to a low value capacitor. So how can we find capacitance? So these are the rules that you can use to find the capacitance. So suppose plus minus Q charge are deposited on conductor's surface. So these are the steps you can take to find the capacitance. So first you find the D, electric flux density. Okay, so this is covered in our earlier lecture. How do you find D? What law do we use? Remember what law we can use to find D? Gauss law. Okay, so we can use Gauss law to find D, which is okay, and then you can use, once you have find D, then you can find the electric field, E, using the relationship D equals to okay, epsilon R, epsilon naught E. Okay. So having found the electric field, we can find the potential. So potential is equals to minus okay, minus integral of the electric field dot dl. And then once you have the potential, then you can find the capacitance from equation 1. C equals to Q divided by V. Okay, so these are the 3 steps you can take to find capacitance. Okay, so this is an example of one of a common type that you can solve using the 3 steps that I talked just now. So you can find the capacitance or calculate the capacitance C for 2 concentric spherical metal shell. Okay, so we have one solid shell or solid spherical shell inside, and then one hollow, and then the radius of the inner one has a radius A, and then the outer has a radius B. The inner one has a charge of plus Q, and the outer one has a charge minus Q. Okay, so if you have a structure like that, then we can work out the capacitance of this structure. So first we want to find the D field between the 2 structure, the inner spherical metal shell pointing towards the outer spherical shell. Okay, so we assume the space here to be A, which means that epsilon naught, epsilon R equals to 1. Okay, so assume that this space is A. So the first task is to find the electric flux density. So we can use Gauss law to find that. Okay, using Gauss law, we find that D will be equals to Q over 4 pi R squared. And then you can find the electric field, which is Q over 4 pi epsilon naught R squared. And then we know that the electric flux density and the electric field are parallel to each other at all points. And then they're points radially outwards from the inner shell to the outer shell. Okay, if you look at the equations, it's also the same equation of a point charge that's sitting at the center of the shell. Except that in this case here, if I have a point charge, then you have electric field going away from that point charge. But in this case, because it is a spherical metal, then the electric field in here is 0. Okay, the electric field starts from the outer conductor of the inner shell. Okay, we work out the electric flux density magnitude and the electric field magnitude. And then we can find the potential. So the potential difference between the inner and the outer shell or spherical conductor, okay, that will be Q over 4 pi epsilon naught A. So we can find the potential, if I call this VA and this VB, reference to infinity. Okay, earlier on we said that for point charge, okay, so V equals to Q over 4 pi epsilon naught R for a point charge reference to infinity at a distance R from the point charge. So in this case here we have VA. This will be my VB. So my potential difference will be my VA minus VB. And therefore, and then we can apply our capacitance equation, or equation 1, which is equals to Q over V. And we work out that our capacitance for this structure will be 4 pi epsilon naught A times B over V minus A. Okay, so that's basically Q divided by Q over 4 pi. And then simplify this equation, we end up with the capacitance 4 pi epsilon naught A times B over B minus A. And you can see that in this equation, so this is the space between them is A. If we fill the space between them with dielectrics with a relative permittivity of epsilon R, then this will become, the capacitance will become 4 pi epsilon 1 epsilon naught AB over B minus A. Okay, so you can see that by putting a dielectric materials in the space between the two conductors, we automatically increase the capacitance by a factor of epsilon R. Okay, so there is a very useful way to increase the capacitance or to increase the ability to store charge by putting a high relative permittivity materials between the two conductors. And we increase the capacitance by that factor, epsilon R. Okay, so that is how you can increase capacitance. Put a dielectric materials in the space between the two conductors. That will increase the capacitance by a factor of epsilon R. Okay, if the radius of the outer sphere become very large, the capacitance of a single isolated conductor sphere will be given by 4 pi epsilon naught A. Okay, if I go back to these equations, if B become very large, okay, so B is very large, then this equation reduced to 4 pi epsilon naught A, which is this equation here. Okay, so you can prove this by taking so if I take B out as a factor, and if B become very large, go to infinity, then this become 0. And therefore you end up with 4 pi epsilon naught A. Okay, so that is when B become very large. So remember our structure looks something like this. A. And then this is B. So if my outer sphere radius become very large compared to the inner one, then we can treat B as infinity, and we end up with 4 pi epsilon naught A. So if the outer shell become very large, then you can think of it as an isolated conducting sphere, just a single sphere. So the outer one go to infinity. Okay, so this is something quite curious, because we have a single conductor's capacitor. Okay, so we always think about capacitor as two conductors, as mentioned earlier on when we start our definitions. We said that we need to have two conductors, put a voltage across them, and now we're saying that we can have a single sphere that can store charge and can be a capacitor as well. But this is not contradicting. We just reference the other side of the conductors to something very far away, in infinity. Okay, so this is referenced as the capacitance to Earth of an isolated conductor. So we have one sphere, the other reference point is to the Earth. And so it's referenced to Earth. Okay, so it's different from earthing the conductor. So if we earth the conductor, we're grounding the conductor. But this is referencing the conductor to Earth. So we have one conductor, and then the other conductor is the Earth. Okay, so that is the capacitance of a single conductor. When we earth the conductors, then there is different thing. We physically wired that conductor to Earth. Okay, here's an example. Find the capacitance of two concentric spherical metal shell of radius 1 centimeters and 1.05 centimeters. What size of an isolated shell do you need to achieve this value of capacitance? Okay, so there's two questions here. One is to work out the capacitance of two concentric 1 centimeter, and then the other one is 1.05 centimeters. Work out the capacitance. And then the second one is to work out if you just have a single to get the same capacitance. Okay, depends how the question is asked. So if the question asks you just to work out the capacitance, you can remember the equation and just put in the value. But if the question asks you to derive it from first principle, then you have to use the 3 steps to work out the capacitance first before you apply the equations. So in this case here, just to find the capacitance, you can apply the equation straight away. What's the equation? C equals to 4 pi epsilon naught AB B minus A. So this equation is only for a spherical metal shell. Okay, it's not for all conductors. So it's geometry specific, your capacitance. So the best is to remember how to derive them rather than remember specific equations. But for specific geometry equations, yeah, it's good to remember them if you can, but it's even better if you can derive them. Okay, if you put in the values, you should get the capacitance equals to 2.3 times 10 to the minus 11 farads, or 23 picofarads. And then for the isolator shell, that shell needs to have 21 centimeters radius to create the same capacitance. So the second one is basically equating 4 pi epsilon naught A equals to 23 picofarads. And A should give you 21 centimeter. Okay, so what this example illustrates that if you have a metal shell of 21 centimeters in radius, so which means that the metal ball is over one feet in diameter, and that only gives you 23 picofarads of charge. Okay, so it's not a very good capacitor. Such a large ball only gives you 23 picofarads. Whereas you can achieve a similar capacitance with something of just 2 centimeters in diameter. Okay, any question? Anyone doesn't know how to calculate this? Pretty straightforward example. So this is more common, parallel plate capacitor. Potential difference is maintained across 2 parallel metal plates. The electric field is approximately uniform in the space between the plate. So if you have 2 plates, so this is a side wheel, assuming that this is my plate. So 2 conductors, apply a potential between them. Eventually we have plus Q minus Q on the 2 conductor. Okay, so what is said here is that the charge density across the inner surface of each plate is approximately uniform. So meaning that my charge is something like this, uniformly distributed, top and bottom plate. And what that does is that it creates an electric field approximately uniform between the space between the two plates. Outside the plate is almost zero electric field because they cancel out each other. Okay, so you can show this using Gauss law. You can do it for one plate at a time. So if I just work out the plate on the top and then work out the plate at the bottom, and then you can do a superposition of the field of the two. Okay, so first you apply your Gauss law and then find out the electric field between them, and then you can find the capacitance of this parallel plate capacitor. Okay, so there is a finite electric field outside the plate, but its magnitude is very small if the plate spacing d is much less than the width W. Okay, so just now our plate separation here is d. The width of the plate is W. So if W is much larger than d, then we assume that the electric field outside is almost zero. So we assume that the electric field is purely between the plate. Okay, so there's small field outside, but we neglect that field because it's very small. Okay. So these are parallel plates. If W1, W2 are much larger than D separation, so this field here is very small. So we only account for the field inside, in between the plate. Okay, so when we calculate our capacitance, we only account for the electric field between the plate, and we don't account for the field outside the plate. And that makes the derivations a lot simpler. Okay, so the charge density of the plate will be Q over A. A is the area of the plate, and therefore from Gauss law we can work out that D will be equals to sigma, and then the electric field will be equals to sigma over epsilon naught if the spacing between the two plates is A. And we know that the electric field going to point from plus Q to minus Q, because positive charge is the source and then negative charge is the sink. And then we can work out the potential from the equations. E equals to minus integral V equals to dot dl, and then because the electric field is uniform across the plate and doesn't change from the top plate to the bottom plate, it's constant, and therefore this integral simply equals to E times D. Okay, therefore the potential difference will be equals to E times D, and therefore the electric field will be equals to V over D. Or V equals to E times D. We can find the capacitance, which is equals to Q over V. Okay, and we know our V is equals to E times D. And then our Q is sigma times A. And therefore, my C will be equals to epsilon naught A over D. And that is the capacitance of a parallel plate capacitor. Again, if we increase or we change the or we put dielectric materials between the plates, then the capacitance will be increased by epsilon R. Okay, so when we put or we fill the space between the plate with dielectrics, then E will be equals to sigma over epsilon R epsilon naught. Doing the same thing here, you find that C will be equals to epsilon R epsilon naught A over D. And this is equations of a parallel plate capacitor. Capacitance of a parallel plate capacitor. Okay, come across this equation before? Parallel plate capacitance? Have you learned this equation before? Or this is the first time you see this? Okay. So A is the area, which is my W1, W2. D is the separations. And then epsilon R is the relative permittivity of the materials you put in between them. And then that is the basic construction of a capacitor. Okay, so there is a parallel plate capacitor with a single dielectric material filling between the plate. Any questions so far? Okay, they're all linked from the earlier topics. So you need to know Gauss' law to find the electric flux density, and then from there you can find the electric field, and then from the electric field you can find the potential difference, and the potential difference now you can find the capacitance. So what happens if we have two layers of dielectric materials? So just now we just have one dielectric materials, epsilon 1 or epsilon R. Now we have two. If we have, so this is my conducting plate. Okay, so if I apply this to a supply, then I'll have plus Q and then minus Q. Top plate will have plus Q, minus Q on the bottom plate. And then each layers of my dielectric materials, T1 and then T2 corresponding to epsilon 1, epsilon 2. From our boundary conditions that we learned earlier on, the electric flux density that go perpendicular to the boundary, the electric flux density is the same over the two materials, but the electric field is different between the two materials. Still remember that? Okay, there are two boundary conditions we learned. One is in this directions, D is the same, and then the other one is in this directions, E is the same. Okay, so we're using this, so D is the same. So D is the same but different dielectric materials. Therefore we have E is different in the two layers. So we have E1 and then E2. And then you can apply the relationship between D and E to work out what is E1 and E2. Okay, so this is basically equals to D over epsilon 1 epsilon naught. Okay, so that's from the boundary conditions. Okay, so D is the same, so it's a constant. So D is equals to epsilon naught epsilon 1 E1 is also equals to epsilon naught epsilon 2 E2, and therefore this and this cancel out. We work out that epsilon 1 E1 is equals to epsilon 2 E2. And with that, we can work out the potential difference. Okay, so the potential difference is the electric field times the separations. And in the first layer, we have E1, T1. Then second layer, we have E2, T2. And you can work out that V will be equals to E1 T1 plus E1 T2 epsilon 1 epsilon 2 using this relationship here. Okay, so and then putting that back into our equation, we can find that the capacitance of this two layers parallel plate capacitance equals to epsilon 1 epsilon 2 epsilon naught A over epsilon 1 T2 plus epsilon 2 T1. Okay, and then if we inverse these equations, 1 over C, and that will be equals to the equation something like this. You can see that this is my capacitance of my first layer, and this is the capacitance of my second layer. Okay, so this leads to your series capacitance equations. So your series capacitance equation is 1 over C total equals to C1 plus 1 over C2. And then my C1 is the capacitance of the first layer, and then C2 is the capacitance of the second layers. So what we have shown here is that my capacitance just now, epsilon 1, epsilon 2, this is my conducting plate. Although there is no plate in the middle, this effect is the same as two capacitors connected in series. Okay, my parallel plate capacitance, I have one layers, two layers, and that will be equivalent to having this one layers as a parallel plate capacitor on its own, connected in series to this layers, which is also a parallel plate capacitance on its own, and that work out to be the same thing. And then C1 is equals to epsilon 1 epsilon naught A over T1. And then C2 is equals to epsilon 2 epsilon naught A over T2. And then if you put this into these equations, you're going to end up with this equation, so which is the same thing. Okay, so the same principle can be applied if you have many layers. Okay, so if some of the layers has A sandwiched between the parallel plate, you just use epsilon r equals to 1. Okay, so if I have T1, T2, T3, T4. Okay, so if I want to work out the capacitance of this is equals to T1, T2, T3, T4. Okay, and then you can use your single parallel plate capacitor for each of this to calculate C1, to calculate C2, C3, C4, and then you just use your circuit theory that you understand of how series capacitance work. 1 over C equals to 1 over C1 plus C2, C3, C4. Okay, so that's how we can extend this two-layer system into multi-layers of dielectric materials. Okay? You follow so far? Okay, should be a lot simpler compared to previous topic. No integrations here. So okay, example. find the capacitance of a parallel plate capacitor of an area 1 squared centimeters of plate separation 1 millimeters if the dielectric layers of the dielectric constants. So dielectric constants is another word for relative permittivity, epsilon r, has an A gap of 0.25 millimeters either side of it. Okay, so we have epsilon r equals to 2.5 with a thickness of 1 millimeters, and at either side of it you have an A gap with a thickness of 0.25, and here is my conductor.
Plate separation means the two plates are 1 millimeter apart.
Sorry?
I thought the plate separation means the two plates are 1 millimeter apart.
Yes. Okay, so this will be 0.5. Okay, the plate that we have just now, we have one dielectric in the middle and both sides with A gaps. So this is equivalent to a series capacitors. So we have epsilon 1 here, 0.5 millimeters, and then this is 0.25, 0.25. And then here epsilon r equals to 1, epsilon r equals to 1. And then this equals to 2.5. So we can call this C1, C2, C3. And we can work out each capacitance. C equals to epsilon r epsilon naught A over D, and D is the separation. Okay, so if you put in the value, the capacitance should work out to be 0.126 nanofarads. Okay, so C1 will be equals to epsilon naught A. A is 1 squared centimeters. And then C2 is equals to 2.5 epsilon naught okay, C3 is equals to C1, and then you can put in 1 over the total capacitance equals to 1 over C1 plus and then Cp will be equals to So 1 squared centimeters is equals to 10 to the minus 4 squared meter. Okay, C2 should be 5 times of C1. C1 should be about 17.708 times 10 to minus 13. No, sorry, my mistake. This is 0.25. So it should be 2 times of this. Okay, you can try that and then see whether you get the same value. So how about this? So if I have epsilon r, and then here is epsilon r equals to 1, epsilon r equals to 1. Okay, so in this case here, this is actually okay, they are in parallel. So you can go back and prove to yourself that it is indeed the case. And to do that, you can apply it. So now the field is in this direction. So what's the same? Is it the electric flux density the same, or the electric field is the same? So just now was this way. We said that the electric flux density is the same. And now the field is parallel to the boundary. And in this case here is the electric field. It's the same. So we have D1, D2, D3. Okay, so follow back the same procedure that I did for the two layers. And then apply it in this structure and see whether you can come up with a formula that is C the total capacitance will be C1 plus C2 plus C3, and C1 is each of the single parallel plate capacitor.